Hello.
Hey, Sydney.
Hi.
How are you?
I am really good. How are you?
Good. The kids are not here right now. That's good. Yesterday they were
I
here.
love that.
They were not so good. They were good for class, for biochem. They were so loud. Oh my God. So they had to go today. Tomorrow it'll be different. So I got to figure out. Only Mickey Mouse can go but so long.
I understand that. Well, not really. I don't have kids. Both my jobs got closed because of the virus, so I've been off for like 2 weeks, and it's kind of really nice.
So what have you been doing?
Dr. Jones, it wasn't good.
What wasn't good?
I just took a physics test.
He gave. Father God, I pray that Olivia has passed that test and she will be fine in Jesus' name. Amen. We pray. So what did he do? He gave it to you guys this morning. How did y'all do it?
He put it up there and we had to do it and take pictures and then upload it. He put it up as a PDF and we had to work it out on a piece of paper and then upload the picture.
I'm doing mine in 2 parts like that, but I'm gonna have my students either upload a picture or they can fill it in the chart because they have to do that. There's a scan app that's on the phones. Let me let me figure out something real. Jenna, I need your address. Can you send it to me?
Oh yeah, I need to send that to you. Yes, ma'am.
So Olivia, y'all had your test today or yesterday?
7 minutes ago. Today.
Oh, y'all have to take it during the class time?
Yeah, because we might do well if we get to take it longer than that.
Well, the way that I'm gonna do you guys, you're gonna have the same amount of time as you have in class. It's just that y'all have to have the test done that day. I'm gonna come on and just explain to you what the test is about, and then that's gonna be pretty much it. But you got to have the test completed by 11:59 that evening. I'm gonna try to see if you guys are gonna have anything to draw or anything like that. He did send me a list of topics that is supposed to be on you guys' final. I'm kind of looking at that now to see how I'm going to pull the questions together. So I'm going to get everything else put up for all my classes, and then I got to work on putting together an online final for you guys that look like a standardized final. So that's going to be my charge for the next few weeks.
Hang on.
I swear I thought I did 14, but we didn't. So 14 is up. That's what we're going to do today. All right. Okay, thank you. I'll send it out.
Thank you.
Mm-hmm. All right. You guys, I am going to cut off my camera. I just want to give you guys fair warning, and then I'm going to go ahead and go through. But if you got any questions or anything, I'm opening up a chat window. Let's see. All right, chapter 14, you guys. So, chapter 14, we're going to talk about conjugation. In chapter 15, we talked a little bit about the p orbitals overlapping. And so that's one of the things we're going to look at. Now here, the p orbitals in the elliptic position is in conjugation with the double bond. So here you see 4 p orbitals on adjacent atoms that makes that 1,3 diene a conjugated system. So why do we care about conjugation? So conjugation can also happen to a point that you can cause things to delocalize. So let's just say you have 3 or more of these p orbitals on an adjacent atom. It allows those p orbitals to overlap and they can delocalize. And so this is what you see here. Basically, the electron density of the 2 pi bonds is delocalized. So basically what happened is they delocalize, and then basically those the electrons can spread out. And so that's why they're delocalized, because there's more coverage or more spread. Now, when you talk about that, you can have different types of dienes. So we just talked about 1,3 diene, but 1,4-pentadiene is an isolated diene. So in this one, the pi bonds in the 1,4-pentadiene are too far apart to be conjugated, and they're isolated from each other by sp3 carbon. So the butyl 1,3 diene, the electrons are delocalized, and then you have penta 1,4 diene, the electrons in the pi bonds are localized, but it's an isolated diene. Now, you can have different types of electrostatic potential plots for dienes. Now, what you can see is with the conjugated diene, you can see where And usually when you're looking at these electron density diagrams, you can see where right here, the butadiene, you can see right there in the middle around the 4 carbons, you can actually see in red where all the electron density is right there in that area. But when you have an isolated diene, where you see is mostly right here at that first double bond where those pi bonds are, that's where you see most of your electron density. So in the butyl 1,3 diene, it's spread over the 4 adjacent atoms. So it's spread over, whereas these are just localized on the pi bond. Sydney, you got your notes? Okay. So let me go back right here. So the allocarbocation is another example of your conjugated systems. So here you see that the electron density in the 2 pi bonds, they are delocalized as well. Conjugation actually stabilizes the allele carbocation. And so that's what you look at. If you got a conjugated system, you're looking for more stabilization. And so that's what these p orbitals do. If they're delocalized, they cause it to be more stable. And that's just because it is spread out. And sometimes spreading out causes more stability. Now, can you have hybrids that are delocalized? Yes. Now, looking at that, you can draw resonance structures from allele carbocations. And that's a way that you can just show that how conjugation really delocalized the electrons. The allele cation is a hybrid of 2 resonance forms. So in the hybrid, the positive charge is delocalized over 2 terminal carbon. So that's what you see there, that partial positive over the over those 2 carbons on the end. So delocalizing the charges stabilizes it. So it stabilizes it more than a 1 degree carbocation. So that's what they're doing. In the hybrid, they're just trying to make sure it is spread out and they delocalize it. Now, why are these cations and why are they stable? So when you look at it, stability often happens when you got more R groups. So that is what's going on. And so when you do that, you actually see that. So here they see from less stable, you got mostly just hydrogens there. And when you increase those groups, those R groups, you go from 1 degree to 2 degree, and even 3 degrees, you increase your stability. And basically what it is that the spread of the electrons will go out more. And that's because if you got an R group, normally it is heavier than just your hydrogens because your hydrogens are much smaller. And so with them being much smaller, what happens is that the electrons are going to be in that area because those atoms on that end are heavier. Now, alytic carbocations, let's look at them in biological reaction. Now, these form from diphosphates. Now, you see these in different types of biological reaction. You see that in general diphosphate, and that is 2 5-carbon substrates, dimethyl diphosphate, and isopentyl diphosphate. So these, when you're looking at your diphosphates, they are mostly precursors or lipids that are in plants and animals. So, so a lot of lipids that form, that's where this diphosphate come in. Yesterday when we was talking about this in biochem, you got a lot of phospholipids that are in there, and these are usually how they generate with general diphosphate. So you usually, in this case, form new carbon bonds. So it includes the loss of the leaving group. And so usually diphosphate leave, and they call it PPI, to form an allylic carbocation followed by a nucleophilic attack with the electron-rich double bond. So that's what happens there. Now, the biological formation of the general diphosphate, this is what happens. You got your dimethyl allyl diphosphate. What happens is you basically you lose the diphosphate leaving group. You get the allylic carbocation. You get your nucleophilic attack of the isopentyl diphosphate. That's what happened on the allylic carbocation. That's where your new carbon-carbon sigma bond forms, and then you get a loss of a proton right there in right after step 2, right before step 3, and that's where it forms the general nil 5-phosphate. Okay. All right. There are different common examples of resonance. You got the 3-atom allele system, X equal to Y minus Z. And so basically, what happens is the allele cation and the acetate anion, those two resonance structures, they differ by the location of the double bond. Either the charge, the radical, or the lone pair is generalized by that little star. And so that's what you see up there, X minus Z, and Z has that star by it. So they says that basically what happens is you got your allylic carbocation, and then you get X, Y, and Z. And usually what happens is you see your acetate right there. And that's what happens. And they were just showing those two. Now, what about double bonds that are conjugated? If they cyclic, completely conjugated rings like benzene, they have two resonance structures. You draw them by moving the electrons in a cyclic manner around the ring. And so we talked about benzene a little bit yesterday in chapter 15. 3 resonance structures can be drawn from other conjugate dienes. And so when you do that, you can always have 2 of them will involve the separation of a charge. So that's what you can do. Now, the third example, you can have cations that have a positive charge adjacent to a lone pair. So when a lone pair and a positive charge are located on adjacent atoms, you can have 2 resonance structures that can be drawn. So you can do that. Now, the overall charge in these can be the same. And now with that, if you go back to general chem and what we talked about last semester, it is based on formal charge, and a neutral X in one of the structures must bear a positive charge in the other one. So usually you gotta have that positive charge. And so the positive charge is adjacent to that lone pair. Now, you can have double bonds that have one of the atoms that is more electronegative than the other one. And so when you have that, you can have a second resonance structure that can be drawn by moving the pi electrons onto the Y. And so what they're showing is, hey, here, electronegativity of Y is greater than X. And so they'll put the positive over the X because the Y is more electronegative. And so you can do that with resonance as well. Now, the resonance hybrid. Basically, the resonance hybrid is just a combination of all the resonance forms. And it just shows basically which one is stable. Now, there are rules that are behind this that look at the relative stability. So one, the resonance structures with more bonds or fewer charges, they are better. Now, resonance structures in which every atom has an octave, that is very important. That's better as well. So the resonance structure in which all the atoms have octaves is better. Even though a positive is placed, charge placed on more electronegative oxygen atom. So just as long, and that's important in chemistry, most of the time, you gotta have that octave over them. Okay. Now, resonance structure that place a negative charge on a more electronegative atom are better, and that's what you saw with the X and the Y. Okay. So what they did here is they put the negative from there and they moved it up here around the oxygen, and that's just because the oxygen is more electronegative. Okay. Now, when it comes to resonance structures and determining them, um, you have A and B, and you got those resonance structures with the stabilized anion. And you see this. So the questions you got to ask yourself is here in the first one, is it sp3 hybridized or if it's sp2 hybridized? So let's look at structures A and B. So on structure A, you got the carbon is sp3 hybridized with the lone pair of electrons in the sp3 hybridal orbit. But in B, however, and it just depends on where that double bond is, it's sp2 hybridized with the unhybridized p orbital forming a pi portion of the double bond. And so that's where it is right there. And so you can have that can happen. So it just depends on where that double bond is in the resonance structure. Now, if you want conjugation, you gotta have p orbitals. That is the name of the game. So the electron pair on a carbon atom adjacent to the carbon-oxygen double bond can only be delocalized if it has a p orbital that can overlap. And so 3 adjacent p orbitals make the anion conjugated. And so the actual hybrid has more of a charge on the oxygen and more carbon-carbon double bond character. So that's what happens there. Now, what about these dienes? A lot of times you have dienes that are conjugated. Conjugated dienes are also called 1,3 dienes. So usually that's what's given. So conjugated dienes, 2 double bonds joined by 1 sigma bond. So 1,3 butadiene, that's the simplest one that you see out there. It got 3 stereoisomers possible from 1,3-dienes. The alkyl groups are bonded to each other end to end, to each end of the carbon of the diene. So here you got trans 1,3-diene or EE 1,3-diene. You got cis or ZZ 1,3-diene, or you got cis trans 1,3-diene or ZE 1,3-diene. So your conjugated dienes are going to have those 2 double bonds, 1 single bond. Okay, there are 2 possible conformation results from rotation around the carbon bond that forms those 2 double bonds. And so you see that you got your S-cis conformation, and then if you rotate it, you got your S-trans conformation. The cis is going to, of course, mean same side. The trans mean opposite side. Now, your stereoisomers, they are going to be very, very unique and discrete molecules where the conformation interconvert. That is what happens. So you got cis, trans, and then you're going to have here for the trans, you're going to have an S-trans. And then you got the trans isomer, and you got S-cis. So you're going to have 2 stereoisomers and 2 conformations when you have that. Now, with the dienes, isoprene, for instance, and isoprene is also known as 2-methyl-buta-1,3-diene, is given off by plants when the temperature rises. And that basically what happens is that is to basically increase the plant's tolerance for heat stress. So usually when it gets really hot like it is now. So the other thing, lycopene. So when you talk about tomatoes, that's the red color in lycopene in other fruits. It's an antioxidant. So this is what you see right here. This is the structure for lycopene. And you see that. So those are some different ones that normally you see or you hear about. Now, what about ones that are biologically active, that has those conjugated double bonds? These are a couple of right here, Zoco and Rocatrol. So what they do is, this one, Zoco, is a cholesterol lowering medicine. And then you got calcitriol is used to treat hyperkalemia, low calcium levels that is in the blood. And you got some folks that have low calcium levels. And so that's what they use to treat it. And so these are 2 active compounds. Now, when you have dienes that are conjugated, what are their features? So you got conjugated and you got isolated. When you talk about the, sorry, I just had to check on that. I sent me something from school. When you talk about the single bonds, that single bond that's in between them, they're usually short. They're not that long. Conjugated dienes, they are more stable. Some of the reactions in the conjugated dienes are different than the isolated ones. And then when you talk about conjugated dienes, they absorb longer wavelengths in UV range. So that's the difference between the 2. So isolated, not so much, but conjugated dienes, they are more stable. Like I said, because they are conjugated, there's more spread than isolated. Isolated just say here, and then you got another little electron density right over here. Whereas which are conjugated, they're in the same place, and the electron density will show right around in the same area. Now, the two things that you have to look at when you're looking at these is percent character and bond length. Now, when you're looking at that, you can look at each carbon atom in a 1,3-butadiene is sp2 hybridized. So when you're looking at that single bond, is overlap of those two sp2 hybridized orbitals, rather than you have the sp3 orbital that's used to forming that carbon-carbon bond. So that's what it is. So usually you gotta look at hybridization to see what is going on. And so that's why we're talking about that. So yes, percent character plays a part, bond length play a part, but that got to be explained through hybridization. Now you got conjugated dienes versus isolated dienes. So when you have hydrogenation of the same alkene from two dienes, the more stable diene has the smaller heat of hydrogenation. Now, when you talk about a conjugated diene, and you see these down here, they are more stable and they are lower in energy. And if you see this one, the penta 1,4-diene, and that's isolated, and then you got your E penta 1,3-diene that's conjugated. You got less energy is being released, and in this case, 7 kilocalories per mole. So that makes it more stable because it releases less energy. So when it comes to conjugated dienes versus isolated dienes, and this is just a graph here that's showing that as the energy goes up. So the conjugated one has lower energy than the isolated diene. And so they're just showing the energy diagram right here. Now, when we talked yesterday, well, on Monday, we really talked about looking at electrophilic addition, and we talked about that benzene, they don't do that. Well, what about these? So electrophilic addition of hydrogen bromic acid into an isolated diene yields one of these products. So you can take an isolated diene and treat it with hydrobromic acid, and then the bromine is going to be on there, and then the hydrogen bonds to the less substituted carbon. Now, when you do that electrophilic addition, it gives you a mixture of products. So it's going to give you 1,2 and 1,4 addition. That's what's going to happen. And so when they do that to a conjugated diene, so it's just isolated, you're just going to get one product. Conjugated, you're going to get two. And that's the difference. So that's electrophilic addition when it comes to your diene. Now here, this is what they said. It's a slow process here, and when it attack it, you get your 1,2 addition. Now here, what happened, the new bonds are shown in red. That happens here, you get your 1,4. And then when you get your 1,4, you show that there are new products. Now, what happens is, in one, your proton of your hydrobromic acid adds to a terminal carbon, and it forms a resonant stabilized acylic carbocation. But in step 2, you got a nucleophilic attack on the bromine at either site. It doesn't matter where it's in that 2 position or that 4 position. And so that's what happens. It forms a 1,2 and 1,4 addition products. So it's going to attack it on either side. So when they're attacking on either side, it's going to form either right there at 2nd position or at the 4th position. Now, the amount of 1,2 and 1,4 addition products form the electrophilic addition reaction. Now, when you talk about the conjugated dienes, it depends on the reaction conditions when this happens. Now, the 1,2 product in low temperature, you'll get 80% of the 1,2 and only 20% of the 1,4. But if you take it and see, that's below zero, that's negative 80 degrees Celsius. Now, if you take it to high temperature, the opposite is going to happen, meaning that you're going to get 20% of the product and then 80% of your 1,4. And so it just depends on the conditions. So what's between 80 and negative 80 and 40? That should be interesting. That should be about, it won't be zero. It's going to either be a negative 20 degrees. And probably where you can get your 50-50. Now, you can have thermodynamic or you can have kinetic products. So, what's the difference between the two? So, when it comes to 1,2, the product at low temperature is kinetic, it's a kinetic product because the 1,2 form faster because it predominates. Now, at the higher temperature, it's more stable because it predominates at equilibrium. And this is called the thermodynamic product. So this one forms mostly 1,4 is at equilibrium. The other one is at lower temperature. So one would be kinetic and the other one would be thermodynamic. Now, how kinetic and thermodynamic products are formed, you got to look at your rates of your reactions. We keep coming back to that. And so here, your lower activation energy, right here, you're going to have a faster reaction. If you got higher activation energy, you're going to have a slower reaction. So that's what it is. You have to look at that. Now, most of your 1,4 products is going to be more stable because it has those two alkyl groups bonded to the carbon-carbon double bond, whereas the 1,2 product only has one. And so that's the big difference. And so the thermodynamic product is going to be more stable. Now, what other effects that can happen? You can have proximity effects for 1,2 products. You can have the kinetic product, and you can have that. So the bromine ion is closer to the C2 rather than the C4. And then the 1,2 addition gives you that kinetic product. And it forms faster because of the proximity of the the bromine ion to C2. So that's what it is for the 1,2 products. Because they're closer together, it forms a lot more. So it doesn't have nothing to do with temperature. It does, but it's more so the proximity. Now, right here is your energy diagram for your two-step mechanism. Now, right here at low temperature, the lower energy of activation pathway is followed since most of the molecules don't have enough energy to overcome a higher barrier. So at higher temperature, the most of the molecules have enough kinetic energy to either reach a transition state, and the equilibrium favors the more stable product. Now, one of the reactions that you guys are going to look at on video is the Dow's outer reaction. It's an addition reaction between the 1,3-diene and the alkene, and it formed a new 6-member ring. The curved arrows are needed to show the cyclic movement of those electron pairs. Okay, so when that is formed, you have a new pi bond, and you got one pi bond, and what happens is the 3 pi bonds break into sigma bonds and 1 pi bond form in this process. Because each new sigma bond is about 20 kilocalories per mole stronger than a pi bond that's broken, this reaction releases about 40 kilocalories per mole of energy. Now, this is some examples of that reaction that are right here. And so the 1,3-diene, dienophile right there, and then that's the Dow's outer reaction. Ooh, so what do you find this at? So the tetroxydoxin, and it's a natural product, got 6 member rings. It's a poison, and it's in pufferfish. So when we go back to the beach and all of that stuff, if you see pufferfish, stay away from it. Not good. It releases a poison, and that can really hurt you. And so that's a Japanese one. So if you see those, because I know people like to bring very strange and exotic things over here to the United States, stay away from it. Not good for you. Now, how do you draw the product of the Dow's outer reaction? So here we're going to talk about that a little bit. Now, you draw the product, how you do it. First, you got to arrange the 1,3-diene and the dienophile next to each other with the diene drawn in the S-cis conformation. No other way, it got to be drawn in the S-cis conformation, showing it that it's on the same side, because that's where it has to join and it has to attack. Now, when you do that, you got to cleave the 3 pi bonds and use the arrows to show where the new bonds are formed. So those double bonds are going to break right here, and then what you have is your dia's product. So basically, it's going to turn into a ring. And so that's what happens. And so that's step 2. The diene can only react when it adopts that S-cis conformation. Now, when it does this, it's only present or prevented in cyclic alkenes. So what happens with that is it's constrained to an S-cis conformation. The diene is usually reacted in. When the 2 double bonds are constrained in the S-trans conformation, the diene is unreacted. So it has to be in a cis conformation, side by side. It is more reactive in that conformation than it is anywhere else. Now, there are rules of this reaction. When you talk about this, I'm pulling up you guys' lab because I'm trying to see when this one was supposed to be done. So that's what I'm doing. Then I'm gonna go back. Now, when you do this, the conjugated dienes, what happens in this reaction? It acts as a nucleophile, and the dienophile acts as an electrophile. Now, the ones that like to take the electrons out of the groups make the dienophile more electrophilic and thus more reactive. And so that's what happens. If the Z is an electron withdrawing group, then the reactivity of the dienophile increases as follows. And that's what you see there, increasing activity. And so, like I said, with this one more compact in the second one, and then the other one is more spread out, and so making it more reactive. Yeah, for this week, yeah, that's what we were supposed to be doing, is the Dow's outer reaction this week. So we're gonna look at that, and I got some videos of that that you guys can see. Now, the dienophiles in the Dow's outer reaction. Okay, so you got acrolein, methyl ketone, maleic anhydride, benzoquinone. Those are ones that you've seen. I think that benzoquinone is the one that we were going to use in there. And so these are different ones. And so it's usually a carbonyl group adjacent to the double bond. That one is an effective withdrawing group because it got that positive, that partial positive charge. The stereochemistry of the dienophile, it is kept, it is retained. So usually that's what happened. So right here with the maleic acid, what happens is it's an achiromethyl compound. I mean, the stereochemistry is still the same if you look at it. It's still a cis product, and that's how it looks, even once it forms that ring. If you look at fumaric acid, this is a trans-dienophile. And what happens is, it is kept. It stays in the same place. So the stereochemistry is kept. It is retained. Now, you can have formation of fused rings. So you can have cyclic and bicyclic system. A cyclic dienophile forms a bicyclic product. So when you have bicyclic systems, two rings are shared a common carbon-carbon bond. That is called a fused ring system. So the two hydrogen atoms that is on there, it got to be in cis formation because there was cis in the starting dienophile. And a bicyclic system is sort to be said cis fused. So that cis setup, the S-cis conformation, it has to be kept. And then when it do that, it can form rings. So it keeps that shape or that stereochemistry. Now, how do these form? And so what happens is, let's just say you got ethylene and it reacts with 1,3-cyclopentadiene. You got a new member ring forms, and above the rings there's one atom. That atom is called the bridge. So thus the product becomes bicyclic, but the carbon atoms shared by both rings are non-adjacent. So the bicyclic ring system with the two rings are shared is called a bridge ring system. So you got this, and it looks like, okay, if you're looking straight down on it, it looks like a 6-member ring. That's what it looks like. And then what can happen is you can have the bridge, and then when you look at it from another standpoint or shape, that's what you see in the last two shapes. So when you have this, you can have the formation of a bridge ring system. So you can have a fused bicyclic system, or you can have a bridge one. So in the fused one, you got one bond in red shared by two rings. And then the bridge one, you got two non-adjacent atoms. And those are the ones in blue, and they are shared by both rings as well. All right. What about this reaction as well. What happens? So it likes the endo orientation. So cyclopentadiene, you can take it and react it with a substituted alkene in the dienophile, the substituted Z. It can be orientated in two ways in the product. It can be endo or exo. So endo and exo. It can be closer to the 2C bridge or the 1C bridge. It doesn't matter. So in a lot of cases, they prefer the Z bridge because they prefer the one product because it's closer to the 2C bridge. And that's just because it won't be as much stereo hindrance. You can also look at the mass of it as well because of weight and how it's being distributed and everything. So they look at it like that, and that can help with it. So they say in a lot of cases, endo is preferred. Now, why is that? And so we have to look at the transition state. When the transition state led into the endo products allow more interaction. And so you got this diene that is electron rich, and then you got the electron withdrawing substituted. Now, when you do that, it kind of balances itself out. Basically saying this one got a lot of electrons over here, this one is taking out some electrons, and then it's kind of balancing. That's why it says it's energetically favorable. And because it's balancing it out energy-wise. Now, there is a mechanism for endo and exo addition. What you can do is look at this from Z under the diene and Z away from the diene, and then there are different mechanisms. And so endo and exo products are formed from the dow's outer reaction, and this is what you see. Like I said, I hate we're not doing this in the lab, and then you'll be able to see this a lot better. Now, to draw your starting materials from the given Dow's outer you got to locate that 6-member ring that got that carbon-carbon double bond. You got to draw 3 arrows around the cyclohexane ring, cyclohexane, beginning with the double bond and the 2 sigma bonds. You got to form 3 pi bonds. And then you got to retain the stereochemistry of the carbon-carbon of the dienophile. The cis substituents on the 6-member ring gives a cis dienophile, and that's what happens there. So retrosynthetic in nature. Now, here you got to look at whether or not you can find the diene in the dienophile. So this is what it is. Identifying the 6-member ring, drawing the arrows, then draw the diene in the dienophile. And you can do it from that, the diels product. So basically what you're doing is with this, you can go forward, you can go backward. But sometimes these things can cause equilibrium expression. So they're just showing you how to look at a diel's Alders product and naturally go back and find the diene in the dienophile. And that's what they're showing here. Now, with these, you can have what you call dimers, and what happens is you got a reactive molecule, like 1,3-cyclopentadiene, it goes this dial's outer reaction very easily. With itself, it can do this on its own because one molecule acts as the diene, and then the other molecule can act as the dienophile. So when this reacts, it takes place so quickly that it only takes a few hours at room temperature for cyclopentadiene to completely dimerize. So you can have that where it reacts with itself and do this. And then you got retrodiodes out of reaction. When heated, you can have it and you can reheat it, and then it can go back. Like I said, it can undergo a reversible reaction and be at equilibrium. So this is how the cyclopentadiene is used in diodes out of reaction is produced. So you got your diodes cyclopentadiene right there, and then it forms that. Now, when it does that, you can take the diene and react it with a different dienophile. And so you can do that, undergo that, redo it, and all of this stuff. So there's a lot of chemistry you can do within this. Now, why do we care about this? Now, a lot of time when we get sick, especially with sinuses and everything, we go and get steroid shots, right? We got to go get that to clear up everything because we get upper respiratory infections and all of that stuff. Now, they use this reaction in order to make those steroids. The steroids are tetracyclic lipids. So usually when they pump you with the steroids, you gain weight. That's because they lipids, they're fat. And they got 3 6-member rings and 1 5-member ring. They tetracyclic. And so this is how steroids normally look. So they're 3-dimensional. They got a carbon skeletal view from the side. This is how they look. So they are tetracyclic lipids, and they got those rings, and they got 3 6-member rings and 1 5-member ring. And so they are large. And so that's why sometimes when people are on steroids, they help you get big. And that's because they actually are lipids and they have a lot of fat in them. Now, there are some common steroids that are out there. So cholesterol is a steroid. Estrone, cortisone, those are steroids. So that's what you get sometimes to calm things down. You get a cortisone shot. Those are steroids. So those are just some example of those you have heard of and you have seen. Now, how do they form these? So it's the same way. You got a diene that has 2 rings on it, and then it reacts with a dienophile that has another ring. And then what you get is the diodes out of product, and then a few more steps, you clean it up and do all that. That's how you get estrone. And then cortisone, you still got that diene, your dienophile, you heat it up, you get a diodes out of products. Then what happens is several more steps, you keep doing it, you get cortisone. So that's what happens. So you use Prevail, the C ring or the B ring of cortisone. That's how the rings are formed. You use the diodes out of reaction. Now, with this, you can also have ultraviolet light absorption. So UV light by molecules can promote an electron from low electronic state to a high one. UV uses a slight shorter wavelength and higher frequency than visible light. UV light, when it is used for that purpose, you mostly have to use it between 200 and 400 nanometers. Now, with ultraviolet light in energy states, what you have to do is the electrons in a lower state or the ground state. So just like the electrons, if they're in a lower state or that ground state, they're moving at a constant but slow speed. And then when you add light, or heat, they get excited and then they are promoted. And the energy difference between the two states just depends on the location of the electron. And then when the electron wants to go back down to that ground state, it's going to give back off that light in the terms of a photon. So that is what happens. And so that's why you see Planck's constant times your frequency there. Now, what about conjugated dienes in ultraviolet light? That's why I hate we're not doing this reaction, because we have been able to use the UV on that. Ugh. So trying right now. So the promotion of the electrons in the sigma bonds and unconjugated pi bonds require wavelength of less than 200 nanometers. So shorter wavelength and higher energy than light in the UV region of the electromagnetic spectrum. When you have conjugated dienes, the energy difference between the ground and excited states, they decrease. So the longer wavelengths of light can be used to promote electrons. The wavelength of UV light absorbed by the compound is often returned as is lambda max, and you see that there. And so, like I said, conjugated dienes and polyenes absorb light anywhere between 200 to 400 nanometers. So how does a UV spectrum look? It's a plot of absorbance versus wavelength. That's how it looks there. The spectrum got very broad bands. The maximum absorbance correspond to lambda max is shown in the UV spectrum of isoprene, and that is right there. I think that one lambda max is 222 nanometers. Now, when you talk about this, increasing conjugation, and when you're looking at UV light, when molecules have 8 or more conjugated pi bonds, their absorption shifts from UV to the visible region. The compound takes on the color of the light if it does not absorb. So it can go from 217 to 268, and then if you add more conjugation to it, it can go up to 364. So increased conjugation, increasing lambda max. That's what happens. And it'll shift, it'll go up into visible region. Now, with visible light, now lycopene absorbs visible light at 470 nanometers in the blue-green region of the visible spectrum. Because it doesn't absorb light in the red region, lycopene appears bright red. So that's what you see there. That's why tomatoes have that nicely red color. Now, the last couple of things we're going to talk about, and then we're going to wrap up. So you have UV radiation from the sun, and then usually it can damage you and prematurely age skin, and it can cause cancer. So what you have to do is, since much of the radiation is filtered out by the ozone layer, only UV light having wavelengths greater than 200 nanometers reaches the Earth's surface. Now, so much of the UV light is absorbed by melanin, and that's the highly conjugated color pigment in the skin that serves as the body's natural protection against harmful effects of UV radiation. So that's what happens. So that's why a lot of times people have to use sunscreen. So prolonged exposure to the sun can cause more UV radiation to reach your skin than the melanin can absorb. Now, commercial sunscreens, they offer sun protection because they got conjugated compounds that absorb the UV light. So commercial suntans, they give you an SPF, a sun protection factor rating, according to the amount of sunscreen. The higher the number, the greater the protection. Now, what sunscreens have in them are aminobenzoic acid, PABA, and it's para aminobenzoic acid, and pentamate O. And so that is what is in sunscreens. And so I'm gonna tell you that PABA is what I'm allergic to. I cannot have sunscreen on with a really high amount of that in there because it burns me for some reason. I have no idea. When I go to the beach, I just try to sit up under an umbrella and try my best not to put sunscreen in. Even if certain chapsticks or whatever have it in there, or even makeup, if it has a lot of PABA in there, I cannot even apply it to my skin. It just burns me for some reason. It's worse than me getting sunburn. I don't know why, but it has happened. You guys, that is it for chapter number 14. When I say turn this off, make sure you subscribe to the YouTube channel. It is Dr. Wanda Jones video classes. All of my classes have a playlist, and your videos are going to be put there in the playlist. Your labs, I am getting ready to look at the videos and put the links to the videos on YouTube and where to find those. What I want you to do, and listen very carefully, I want you to look at the labs that I gave you, and then you're going to watch the videos. And what you're going to do is look at what did they do, how did they talk through it, everything, and how they made it. And then you're going to write your report up just as if you was there doing it yourself, based on what I gave you and based on what they do in the actual lab itself. So some of the videos, they should not be that long, about 15 to 20 minutes. So you can sit there and do that. And like I said, we're just going to go ahead. I'm going to open up those, and you can submit those pretty much at any time. But I'm just going to keep them on a week by week basis. As far as your next exam, we just got to do chapter 16, and then once we're done with 16, we're going to have our next test. We're going to do 16 on Monday. That is my plan, and we should be ready to have a test, hopefully next week. What I am going to do this week and try to finish up is give you some quizzes on these chapters, so you can go ahead and see what's going to be on the test. Like I said earlier, Dr. Craig did send me a list of topics that is going to be on you guys' final. I don't know if we're going to go back to school or not. To really be honest, in my opinion, I don't think we should be going back right now until this thing really goes away. But other people want you guys back. I kind of got mixed feelings on that. But if we don't, I will give you a list of the topics so that you can be preparing for those. Make sure you go ahead and get the ACS book. If you have not, it's an ACS book for you guys. Make sure you go ahead and get the book and start looking at it. Like I said, over the next couple of weeks, I am going to be putting together your final exam. Like I said, I got the topics. I'm going to look at them and kind of put together your final exam based on that so that it can go online. So it's going to take me a little while to build that. Your test, your multiple choice part is going to be online. I'm going to turn my camera on. Hold on. Your multiple choice test is going to be online. The test is going to be in possibly 2 parts. So the multiple choice part is going to be graded just like you get it done with your quizzes. If there's a part that you guys are going to need to write out or whatever, you'll be able to type your answers into that, or like y'all did with most of y'all did with Dr. Issa, you're uploaded. But when you get your exams, if we have the exam next Wednesday, what you're gonna do, you're gonna have that day to take the exam. I know Dr. Craig wants y'all to probably take it during that hour, but what I'm gonna do is open the exam up. I'm gonna come on and tell you this is the exam, this is what you're gonna do and all of that. That's basically gonna be it, probably 10 minutes at the most. I'm gonna open the exam up. You're gonna have until that night to take the exam. Because I know you guys got other classes, other things going on, but you have that day to take the exam. Now the exams are going to be timed based on the class. So what it is that the test opens up at 9:30 or whatever. When you open your test and start it, you're gonna only have that hour and 20 minutes to finish it. That's it. So once you start it, you can't pause it and go back. You have to sit down and do it in one sitting. So that's how I'm setting it up. So I want you guys to be aware of that. So it's going to be done. It's going to be done in pretty much one sitting. That part 2 or whatever is going to probably be about 20 to 30 minutes, not even that long, no more than maybe an hour on that. So give you enough time to do it and turn it back in or to type in your responses. That's how it's going to look. That's it. Questions, comments, concerns you guys may have. Turn your mic on, Jenna.
When is like what are we gonna do for our paper? You know, we have that end lab paper and like presentation. How are we doing that?
That is a very good question. Y'all gonna still do your research paper and turn it in. The presentation part, I may have you guys actually do a voiceover PowerPoint. So basically what you're gonna do, just like what I'm doing, and you can do that in PowerPoint. And hold on, let me put it on this. Okay. If you can see it, my screen, let's see where it is, present online, right there. It says record slideshow. You can actually record it. So you can set it up and do a 5 to 10 minute recording on your presentation. And then you'll just submit it. I'll probably put it on a Google Drive or something like that and give you guys to my Google Drive so you can submit it that way. I don't know if it'll come through Canvas that well, but it'll probably come through better on a Google Drive or something like that. And I'll just have you guys to upload it to that. I think that would be the best thing to do. But yes, you're going to still do it, still do your paper. You're going to still do your presentation. It's just that it's going to be a voiceover. So,
Sounds good.
Yeah, that's the way we're going to do it. So you're going to still do it. Like I said, I'm going to sit right here once I end this while y'all while the video is converting. And I'm going to go in and go ahead and upload the videos for the labs. Like I said, I'm going to open all of them up today, tomorrow, this week. If you want to go on and do them all at one time, that's perfectly fine. If you want to do them week by week, that's perfectly up to you. Doesn't matter to me because I know people got other things going on. They're probably trying to work and all of that stuff, and kids and all of that. So this right here can be quite difficult. Like I said, Monday and Wednesdays I can scoop the kids away. Tuesdays and Thursdays, not so much. They have to be here because I don't have anybody to watch them on Tuesdays and Thursdays. So usually they're upstairs, and normally somebody comes over and watch them because they can't go away. So so we'll work through it. But what I'm gonna do is I'm looking at all the labs, and I don't want you guys So to get us back on track, because we didn't do this tie beam one, but I gave you one. The Boronal, we didn't do that. This week's about EOS out of reaction. So these three reactions, three of the labs, I'm gonna put those due. To give you guys enough time. You need to have all of the labs in by I'll just say the 22nd. But your lab practicum is technically supposed to be on the, wait a minute, let me go to the next. Yeah, so what I'm gonna do is all of the labs, I'm gonna open all the labs up. You need to have all of your labs done by the 22nd, and then your lab practicum presentation is gonna still be due by the 29th. So that's what I'm gonna do. So I'm gonna open all of the labs up. You just gotta have them done by the 22nd, and then you have a week to do your lab practice. So to make it easier on you guys and me as well, just have all your labs done by the 22nd, and then your lab practicum presentation need to be done by the 29th. Will that work with everybody who I have on so far? Okay. All righty. Well, you guys have a good one. We are doing chapter 16 on Monday. I'm gonna try to go ahead and try to put your labs up before I go get the boards or get half of them up. So let me do that. And if you guys got any questions, shoot me an email. Let me know. All right. Okay, you guys. I will see you guys later. See you on Monday.